Welcome to this explainer. I am absolutely thrilled to have you here today because we are unpacking a literal paradigm shift in how we think about artificial intelligence and computing power. Now, for a long time, the model has been pretty simple, right? You rent disposable compute tokens to get answers. It's exactly like perpetually paying rent on an apartment versus building equity in a house you actually own. But what if you could build a durable, local capability that actually gets cheaper and faster over time? Well, that is the exact premise of the Edge Cape Beast architecture. We're going to explore its central thesis today, which is known as the inference economy inversion.
Okay, let's just dive right into it. The old way of doing things is the cloud abstraction. We basically rent raw compute, vCPUs, memory, tokens, for disposable service calls. And the crazy part is, every single time you ask a question, you burn tokens, even if you ask the exact same question tomorrow. The new way is the commons abstraction. Instead of virtualizing physical resources, Beast virtualizes repeated reasoning. It literally turns repeated context selection, tool choice, and verified routes into what we call crystallized compute. Think of it as bottled AI memory. It's a massive fundamental shift from just consuming disposable answers to actually building verified local assets.
Here's our boot sequence for today. We're going to cover the economy inversion, check out the Beast commons, climb the compute escalation ladder, break down the action IR split, run the tiny llama gauntlet, and wrap up by harvesting the swarm commons. Let's get into it.
Section 1. The inference economy inversion.
So if traditional platforms are always asking, hey, what can you run if you rent enough compute? What should a more sustainable system be asking? The answer is the inference economy inversion. It treats probabilistic compute, meaning calling out to a large language model, not as a throwaway service call, but as a governed intervention. When you reduce uncertainty and solve a problem, that solution becomes a verified fingerprint-bound local capability. So instead of burning tokens on the exact same queries over and over, you're turning that uncertainty reduction into an accumulating, reusable local asset. The entire economic unit shifts from tokens consumed to verified work safely stored.
Moving on to Section 2. Beast Commons Compute Spaces.
So, you might be wondering, where does this new economic unit actually live and how is it traded? Welcome to the Beast Commons. And the currency here? Crystals. Now, Crystal isn't just a snippet of code. It's a verified local compute asset. It has a completely proven history, a specific fingerprint of what it impacts, exact criteria for when it can be replayed, and super strict cost accounting. The Beast Commons isn't just another model zoo packed full of text generators. It's a literal exchange for these crystals. We are talking about verified routes, repair patterns, and workflow fragments that actually displays future compute rather than just consuming more of it.
Follow the life cycle of how this works. It starts with a probabilistic provider call, but instead of just vanishing into the ether once you read the output, it hits a conversion ledger. From there, it enters a verifier sandbox where it is rigorously tested. We're talking both visible and hidden tests. If it passes, that verified residue condenses into a capability crystal. That crystal is then stored in the capability treasury as a highly durable local asset. The next time the system sees this exact same problem, it doesn't need to guess or call the cloud at all. It uses zero-call reuse, relying entirely on the stored crystal.
Section 3. The compute escalation ladder.
So who actually decides when to use a stored crystal and when to ping the cloud? That'd be the compute governor sitting right dead center in this governance stack. This thing is the brains of the operation when it comes to cost and efficiency. Before ever reaching out to a cloud provider, the compute governor strictly asks, wait, is inference mathematically necessary here? Can we just reuse a verified capability? Could we do a deterministic local transform? It only escalates to the cloud if there is unresolved semantic ambiguity, meaning the system literally can't understand the context without a massive brain to help it out.
And here is exactly how that escalation happens step by step. Honestly, it acts kind of like a highly frugal financial advisor that actively resists spending your money unless it absolutely has to. Step 1 is entirely deterministic. If a simple local code transform can do the job, boom, it stops right there. Step 2 checks for chronicle reuse, meaning it looks for a past crystal. Step 3 utilizes an Llama Scout, which is a tiny local model. Step 4 escalates up to a cheap, specialist cloud model. And only at Step 5, if literally everything else fails, does it finally call an expensive frontier coding provider.
All right, Section 4. Action IR strategist split.
Now this is where a super strict separation of powers governance treaty comes into play. Planning and doing are completely separated here. Hermes acts as the overarching coordinator. OpenClaw inspects and plans out local first work, And then there's zero claw, which is fascinating because it only plans and is explicitly forbidden from executing any tools whatsoever. Finally, you have Nemo claw, the approval-gated executor. It is the only role legally allowed to act on the system, and it requires explicit approval gates to do anything. The strategist makes the plans for sure, but the executor is kept on a very tight leash.
Section 5. The Tiny Llama Gauntlet.
Okay, enough theory. Let's look at a hard flex using a micromodel, specifically Quen 2.50, 0.5b. 0. That is the explosive metric here. Exactly 0 cloud calls were needed by a tiny 500 million parameter local model to successfully initiate and complete a hard gateway repair. 0 cloud tokens burned. I mean, think about the massive size of normal cloud models and then realize a micromodel just pulled this off.
How on earth is that even possible? Well, check out the assertions passed. The baseline failed, sure, but the live local model attempted the repair, passed verification, got an approval receipt, and did all of this without a single cloud model being touched. It achieved a 100% success rate entirely locally. And let's be clear, this isn't because the tiny model is some magical genius. It's because Beast supplied the orchestration, the structure, the memory, the tools, and the verification gates. Beast wrapped the tiny model in so much governed structure that it literally couldn't fail.
And watch how this efficiency compounds in real time. If you track the cloud calls, you'll see that at occurrence 1 and 2 of a problem, the system totally relies on the cloud. But by occurrence 3, those cloud calls plummet right to 0. At the exact same time, the deterministic 0 call reuses spikes straight to the top. The system is learned. It crystallized the capability. Across 6 different task families, cloud calls completely vanished by the 3rd time the system encountered the problem.
Last up, Section 6, Harvesting the Swarm Commons. So how does Beast scale this localized learning across an entire ecosystem? By harvesting the swarm commons. Think of it kind of like crowdsourcing a map of a minefield. Every swarm run leaves behind a trace. A swarm run is no longer just some invisible back-end detail, it's a reusable compute artifact. Beast harvests incredible evidence from every run, which roles were activated, which profiles were deemed safe, the signals from local scouts, and crucially, which actions the compute governor suppressed versus allowed. This takes inference from just generating text and turns it into actual operational memory. The system is actively learning which role lane sequences are useful for specific tasks. But wait, it's not just about successes. The concept of negative capability is absolutely vital here. Negative capability is the memory that a specific provider, route, or task repeatedly failed. Think of it like touching a hot stove. You don't need to do it twice to learn, right? Well, Beast crystallizes these failures too. Instead of blindly retrying and wasting tokens on known dead ends, failure becomes active routing intelligence. It completely prevents the system from burning compute on paths it already knows don't work.
Which leaves us with this final, pretty provocative thought. In a world where AI electricity demand is absolutely skyrocketing, and we are constantly paying for the exact same probabilistic tokens over and over again, we have to change our mindset. The inference economy inversion gives us a way out. It asks us to look at our workflows and ask, what useful work can you stop recomputing? Think about the operational cost of your own disposable inference and imagine the massive potential of storing that capability locally instead. Thank you so much for joining me for this explainer. Keep learning and keep asking the right questions.